the system is certainly non-quasi-static. It's not in equilibrium. I mean, suppose I ask the question, what is the pressure during the process? What is your answer? Suppose you say, okay, let me do an experiment. Let me put a pressure sensor right here at some point on the wall. I will measure some pressure, local pressure. But is that pressure going to be the same as the pressure measured by over here, for example? No. It will not be the same. There will be some other local value of pressure. Will that be the same as the pressure measured over here? No. So you clearly do not have pressure as a thermodynamic variable, because if pressure is a thermodynamic variable, it should have one value, mean value throughout the, it should have one value throughout the container. Right? What is the system? The system is the gas. And what is the surrounding? The walls of the container. Yeah, let's assume there's nothing outside, just the walls of the container. So there's a system, the gas, and the surrounding is the wall. So this intermediate step is problematic because pressure is not well defined here. Of course, the final state is okay and the initial state is okay. So I can write here that gas, the system, passes through non-quasi-static states between the initial and the final equilibrium state. That statement is okay. The question is, what do we do with this experiment and what do we do with the first law? Suppose first law, so first law is your delta U is Q plus W, right? Now, look, first law is true whether the process is quasi-static or non-quasi-static. It's always true, it's just the conservation of energy. But to use it in practice, I will have to ensure a quasi-static process, because otherwise how will I write W? So how will I write dW is minus PdV? If P is not defined, then I do, what is the meaning of writing dW is minus PdV? So the question is, how are you going to use this first law? But in this process, the free expansion, because you have rigid wall, no work is done. Well, the wall is not moving outwards. There is no change in volume of the container, for example. Suppose it was a flexible wall, imagine. Maybe you could have the walls bulging. Then some work will be done by the gas in pushing the walls outwards. But because the walls are rigid, no work is exchanged between the system and the surrounding. So work done is zero. The process and the walls are adiabatic. So there is no heat exchange. So Q is zero. So delta U is zero. That means in this free expansion, the internal energy, initial value of the internal energy is the same as the final value of the internal energy. I did not say, I repeat, I did not say that internal energy is constant. I don't know what is happening during the process. All I can say is the initial value of the internal energy is the same as the final value of the internal energy. So this is all there is. This is the free expansion process. Now you can ask an additional question. What about the temperature? Is Ti equal to Tf? Because that's not answered from at this level. So the answer is, for an ideal gas, Ti is equal to Tf. I will show that right now. But for a non-ideal gas, Ti is not equal to Tf. That means for a real gas, Ti and Tf will not be the same. Okay, I hope that is clear. So this is the free expansion process. Now I just said that for an ideal gas, Ti is equal to Tf. That is easy to see because you have just shown that for an ideal gas, the internal energy is only a function of temperature, right? And the initial state and the final state are ones of equilibrium. Therefore, the temperature has to be the same. That's all. But for a non-ideal gas in general, what you will get is a relation that looks like this. That UF PF TF is UI PI TI in general for a real gas. And in practice, TF will be less than TI. I mean, for most real gases, we will see under what conditions this is true. But it's for most realistic situations, you will find that the final temperature is less than the initial temperature. And this is what is used for liquefying gases. Right? You can envisage using the free expansion process to liquefy a gas, because You can imagine that if I do this process and the final temperature is less than initial temperature, I can turn the gas back and send it back into the one side of the piston, right? And I can again do the process. So if I can do this in a cycle, I could think of keeping on reducing TF until the gas liquefies. So this is what will be used later. This principle for liquefying gases. Okay, but we'll discuss that later. Now the other process I want to discuss, which is as important, is the throttling process, also called Joule-Thomson expansion. So that system looks like this. I have gas in this kind of an arrangement with a piston here. Let us say the gas is there and the initial state is one of equilibrium. So pressure is Pi and volume is Vi. And the final state looks like this. So this piston has moved outwards. Final state is some pressure is there, Pf, and the volume is Vf. So initial final states are one of equilibrium. What is the intermediate boundary here? This wall. This is called a throttle. So what is a throttle? Throttle means you have a porous wall. So imagine a wall with very fine holes in it. That's a throttle. That's a throttle. Or you could think of a wall with a narrow constriction. Right? So maybe something like this. Let me draw it here. Okay, so I have a thing like this, suppose. You're getting? There is some narrow, so this is let's say P1 V1 here, P2 V2 here, and this is the constriction. So gas is going to be sent through this, pushed through this constriction. Or you can think of this as a wall with fine holes in it. A porous wall. That's the meaning of a throttle. Go back to the figure. All right. Now, we assume that again the same as free expansion. We assume the wall is rigid and the wall is adiabatic. Same for the throttle. Throttle region is also having rigid walls, adiabatic walls. Now, how is the process carried out? This Joule-Thomson expansion is carried out in a special way, special manner. The way it is done is as follows. You have to push this piston in, that means towards the right, and push out this piston also towards the right, in such a way that the pressure is always held constant on one side. That means pressure is always Pi Vi on one side. Sorry, pressure is always Pi on one side, and the pressure is always Pf on the other side. Volume will vary, of course. Is that clear? So the intermediate state is not drawn here, but what I'm trying to say is, imagine moving. Actually, so the picture I had drawn is, if you like, the intermediate state. So let me show the picture here. This picture. This is an intermediate state, right? Pressure is always held constant to Pi here, and pressure is always held constant to Pf here. Because this is some intermediate state. This has moved in some amount and this has moved out a certain amount. This piston. Pressure is held fixed to Pi and pressure held fixed to Pf, but the volume will of course vary and the temperature will also vary. So this is the intermediate step. Finally, what happens is this will come in all the way. What is the system? Now I will choose the system to be the gas outside the throttle. So what I mean is, I will choose, okay, so the figure is a little messy, but suppose I make a box here. And I will say my system, choice of system is up to me, is the gas here and here, but not the gas inside this constriction. Why? Because inside the constriction, system is non-quasi-static. Yeah, because it is going to accelerate. There's going to be turbulence in this region. There's going to be frictional losses in this small region. So this region is not considered as part of my system. System is the gas, excluding this throttle. All right. So what I want to do is, of course, use first law now. What is dq? dq is always 0 because the walls are adiabatic. So question is how to calculate the work done. Nothing, just as minus PdV. Can we calculate this? Yes, we can, because this part of the system and this part of the system has well-defined pressure, which is always Pi. So this is a trivial integral. It just becomes minus Pi from Vi to 0 PV for the gas on the left. What happens to the gas on the right? That is minus Pf Vf to 0, or the other way, 0 to Vf dV. So the network is this plus this. Calculated here. What is the work done? Minus PdV. 0 to Vf, and this goes from Vi to 0. So you can do the integral because the pressure is held fixed by experiment. Experiment is such that the pressure is held fixed on both sides. So just take it out of the integral and you get this object, PFVF minus PIVI with a minus sign in front. Okay, so what is work done? That is change of internal energy, because dq is 0. That is equal to minus PFVF minus PIVF. So let us rewrite this. And what do you get? UF plus PFVF is equal to UI plus PIVI, and that defines the enthalpy of the system. Let me define an energy called the enthalpy, which is this internal energy plus PV. And that enthalpy is the same. The initial value of the enthalpy is the same as the final value of enthalpy. I make no claims about the value of enthalpy in the intermediate steps, because in intermediate steps it could vary. All I'm saying in this is HI is equal to HF. What did you say in the previous free expansion? You said that UI is equal to UF. So internal energy at the initial value is the same as internal energy at the final state. In this experiment, it is the enthalpy which is initial value is same as the final value. So now you might ask, why should we define this? Because as you will see, it's very useful in problems and also very useful in practice. Okay. Of course, it has the same units as energy because it is U plus PV, and both of these are energies. So the unit will be just joule. All right. So let's write DH. Differential of DH is DU plus PdV plus VdP. Right. And what is DQ? And this is your first law. DU is DQ minus PdV. So plug in DU here. So PdV cancels, and you get the differential of the enthalpy, which is DQ plus VdP. Okay, simple algebra. So what happens at constant pressure? This term drops out. Divide both sides by dt. What do you get? dq by dt at constant pressure, which is Cp. So Cp is del H by del T at constant pressure. Do you see what I'm getting at? Let me write down to remind you once again. For any hydrostatic system, Cv is what? Del U by del T at constant volume. And what is for any hydrostatic system Cp? Del H by del T, constant pressure. This is true for any system whatsoever, not just ideal gas. I mean, ideal gas will be easy because U will only be a function of temperature and H will also be only a function of temperature. So this will become ordinary derivatives for an ideal gas. But these results are true for any hydrostatic system whatsoever. Right? So CV will be a derivative of internal energy, while Cp will be a derivative of the enthalpy. That's why we defined enthalpy. I just answered the question. Why do we define it? Because it directly relates to Cp. Remember what I said. This is experimentally measurable. This is experimentally measurable. What is on the left hand side, sorry, on the right hand side will come from some theory. Finally, the theory has to match the experiment. This equation will give you the matching because your theory will make a prediction of this value. An experiment will give me the value of Cv. Right? What is Cv by definition? dq by dt, constant volume. That can be measured experiment in the lab because dq can be measured and dt can be measured. So this can be measured in the lab. This side will come from some theoretical explanation. Same for this. What is Cp defined to be? dq by dt, constant pressure. So this is very, very useful, enthalpy, because it connects experiment and theory. And it comes out rather naturally in the throttling process. That's why I discuss the throttling process. I could have directly started from here. I could have just said I'm just defining a new energy H which is defined as U plus P. But you will not get any feeling for why on earth this has been defined, right? I could have just not discussed throttling. I could have just done this part. Then it would be an exercise in algebra. But I have not done it that because I wanted to discuss throttling process. Throttling process directly tells you that there is some quantity called the enthalpy. It arises out of the experiment. This came out of the experiment naturally. So that's why I discussed the throttling process. And of course, if you have something like this, you can integrate on both sides, provided you know how Cp varies with temperature. Right? And incidentally, in the past, you have heard of this word latent heat, right? What was latent heat? I'll just be back in a minute. So coming back, you heard of this word latent heat. You can now see what latent heat is. It is nothing but delta H, right? Because in doing this integral Cp dt, I'm holding pressure constant, right? Remember your PV diagram. PV diagram, right? That looked like this, right? Something like this. This region, what is this region? This was the region of first order phase transition, right? Condensation or evaporation. What was happening to the pressure here? Pressure was constant. And what was the temperature? Temperature was also constant because this is an isotherm, right? So basically what I'm saying is the changes that are occurring in this, energy changes that are occurring in this region, in the first order transition region, are exactly captured by the enthalpy, change in enthalpy. Okay. During an isobaric process, constant pressure process. So you have seen this in some other form. Okay, I think I will continue with this next week because I want to then get back to first law and do some problems. At least 5 problems I will do next week. So this is enough for today. Wednesday is Republic Day. So what I will do is I will log in anyway, and if you have any questions about the material covered so far, you can ask, but it's optional. All right. Otherwise, we'll meet directly on Friday, next Friday, and we will do at least 5 problems on first law using the tables. So be comfortable in using the tables by next week. Any questions?
Sir, will you share the slides with us?
I can't hear what you're saying.
Sir, will you share the slides with us?
No, the slides are almost exclusively from Sontag or Zimansky. So I encourage you to read the book, and that's the intention of all this exercise, right? Because what I'm doing is discussing the basic facts, but there are a few more details which are given in the book. So I want to encourage you to read it. Any other questions?
So like I was solving other questions and there were questions about other like substances which were not there in the tables as well. So like
Really, materials which, okay, so don't worry about materials which are not given a table at the end of Sontag. I think around 3 or 4 materials are discussed: carbon dioxide, ammonia, carbon, water, etc. But if you get any other material, then you can solve the problem provided you are given the table or you're given the exact values from the table. If neither of them is given, then you are not expected to worry about it. Okay.
okay, sir.